Hello world, here's Jorge and let's continue learning about object detection in PyTorch. In the last video, we saw how to define the function called angular bending. So this function, what did it do? Well, this angular bending function took our oriented gradients, that is gradients that have both basically positive and negative orientations, and essentially yielded a classification of these gradients depending on the say angle that they had associated to. So for example, say we had a 30-degree gradient, so after passing through this angular bending function, the magnitude of this particular gradient would be distributed smoothly between its closest neighbors. So remember that we are basically working with the number of orientations equals to 9. This means that we need to divide the 360 space angle between 9, and that means that we end up with angular bendings of 0, 40, 80, and so on. And so essentially in this particular example of 30 degrees, we would have to look at 0-degree bend and 4-degree bend. So essentially the magnitude of this 30-degree gradient is going to be distributed between the 40-degree bend and 0-degree bend, and of course there's going to be more magnitude of the 30-degree going towards the 40-degree bend, just because of course 30 degrees closer to 40, that is to 0 degrees. Okay, but yeah, that is what we did in the last session, and today I'm going to talk about so-called block normalization. Okay, so what is this going to do for us, the function that we are going to define today? Well, the purpose of this block normalization function is actually going to normalize the gradient magnitudes of say the given spatial region. Okay, and we're going to be working with 2x2 blocks, as we'll see. So essentially the output of the block normalization function is going to be a normalized representation, okay, of our original gradient information. All right, but yeah, let's actually start seeing it in action. And to get started, just let me import torch and import NN as well. So NN, okay, and we are going to, just for purposes of illustrating the point in an easier way, we're going to set the number of orientations to be equal to 2, just for the sake of clarity. Yep. Just to get started, let's just create a random tensor. Let's just create a random tensor with the appropriate shape. All right. So let me call this tensor, say, a random cell, and let's create it. Random, and we're gonna have a tensor of the following shape. We're gonna have, okay, just one input channel, then we're gonna have as output channels 2 times the number of orientations, because remember that for now we are dealing with both positive and negative oriented gradients, because we're coming out of the angular bending. So that's why we still use the 2 times number of orientations. And just for now, let's set the kernel to be a 3x3, or basically to be a 3x3 size kernel. So essentially, that is what we're going to be playing with. All right. Okay. So now let's think about it, and just so that we see clearly what's going on, after I go through the say code, I'll put an explicit example. Okay. All right. So just let me visualize this first. So random cell, just a completely random tensor, exactly just like that. And now what we're gonna do is to start storing certain parts of this tensor. So basically we're going to slice, we're going to basically get slices of these original random tensor. Okay. And to do that, let's write explicitly. So I'm going to write here the magnitudes. Basically this is going to get us, or get for us, the magnitudes of the first half of the gradient that we see right now. So the complete gradient, that meaning is going to take these first two parts, also basically the first half of these gradient magnitude. Okay, or the collection of these gradient magnitudes. So the magnitudes of the first half gradients. Okay. So essentially, this is going to. So how can we code this? Well, essentially, what we're gonna do, because look at this, we have basically four tensors here. Okay, so basically we have, of course, four, say, rows. Well, essentially this is a tensor, right, by itself. What I mean is that there are four rows within this overall tensor, right? So essentially what we are going to do is to tell him, okay, the first two, so the first two, we could also call it batches, right? The first two batches of 3x3 tensors, these are going to represent the first half of the magnitude gradients. And essentially in our jargon, this is going to be the positively oriented gradients, because essentially with these operation here, so taking the number of orientations and multiplying by 2, what we're doing essentially is, okay, I'm going to give you two gradients that are going to be oriented in a certain way, and I want you to also include its essentially opposite parts. So for example, say we input two gradients, that one is having 0 degrees associated to it. Okay, so it has 0 degrees, and the other one has 90 degrees. All right, so with these operation, we are also taking into account its opposite counterparts. That meaning that we also take into account the 180 degree gradient, and we also take into account the 270 degree gradient. Okay, so that is the main idea of these basically multiplication of this scaling factor of 2. Yeah. So with, but let's actually write down the code itself. So we're going to write the following. So we are going to have, well, actually, because we called it random cell, so random cell, and we're going to slice through this random cell. So it's going to be basically we want to take the, say, original, you could call it number of batches as well, because I mean, let's actually recall the shape of what it means, right? So we have number of batches, we have output, so output channel. Well, number of batches really is like input channels, so input channels, output channels, and the kernel height and the kernel width. Yeah, so that is the essentially, let me comment this out, this is the overall shape meaning. Okay, so essentially we want to take the original input channels, we want to take and now this is where we need to be careful, because here's where we need to slice, yeah, because this is the actual split that we want to actually perform. So what we want to do is the following. We want to take the entire, so all the gradients, all the magnitudes of the gradients that are allocated in the first two orientations up to half of it. So basically it's going to be everything up to these number of orientations. Okay, great. And now for the rest, well, we want to keep the exact same shape of say the original tensor. So that is why we are going to just stop it there. Well, and just for the sake of clarity, state that this is height and this is width. So essentially this is the shape for the first half, and well, analogously we can do or we can obtain the second half of the magnitudes of the gradients. Okay, so basically the opposite gradient directions. Okay, so with to do that, so opposite gradient directions. So random cell, and we're going to have the following. We're going to have exactly the same, but now we're starting from the half that we stopped previously, and we're going to end it basically at the end of the, say, collection of magnitudes. So what we need to do now is, okay, we stopped at number of orientations, and now we need to continue till the end. Okay, great. And now, well, we simply keep the same height and width. Fantastic. So now, what could, or how could we move on? Okay, so essentially now what we want to do is to combine this information in order to obtain the unoriented gradients, because actually what we want to do here, yeah, let me place it here so that is clear. What we want to do with this set of operations is to obtain the unoriented gradients. That is basically gradients that are not taking into account the orientations of the gradients. Okay, so basically we can obtain these unoriented gradients by adding the basically magnitudes of both positive and negatively oriented gradients. Okay, and why are we doing this? Well, because remember that our goal is to define a histogram of oriented gradients. Yeah, more specifically, basically a feature that is able to describe those, and typically those are using unassigned gradients. That meaning that the both positive and negative orientations, or better say opposite directions of gradients, are treated in the same way, so as being basically positively oriented. Okay, and basically, just to put another example, so imagine we have a 45-degree gradient, so a gradient that is pointing at the 45-degree angle, and basically we have its counterpart that basically is 225-degree gradient. Okay, so a gradient also pointing now in the opposite direction. So basically with this operation, what we are implying is that we want both gradients, so the 45-degree and the 225, to be both contributing to the same bin. Okay, that is our goal, that both positively and negatively oriented gradients both contribute to the same bin. So to do that, we need to generate these unoriented gradients. All right, so that is exactly what we're going to do now. So let's combine both. So obtain unoriented cell. Okay, so basically we're going to get this unoriented cell, and we just simply need to add both up. Okay, so exactly, so that, and well, whoops, great, like that. And well, let's actually have a look at that. So we're gonna have we go on to combine both positively and a negative gradients. Okay, to get the unoriented to get the unoriented gradients. Okay. All right, great. So now let me just place here the result, and we can have a look at it now. Okay, great. So now let's have a look at this. So well, first of all, let me put a space in here so that we can visualize it in a more neat way, and also let me do the same in here. Great. So this is the tensor, right? And as you can see with this operation, well, we got first the so-called positive part and the negative part. And what did we do now? Well, we just added them up. We just simply, what we did was to add every single magnitude of the gradient, of the corresponding gradient together. So for example, to obtain this number, well, we just simply need to add this number highlighted here with the equivalent position in the negatively oriented part. Okay, and in that way we obtain everything. Great. That is how we obtain the unoriented gradients. Okay, great. Once we have done that, well, the best thing we can do is to create, say, a way to aggregate this graded information. Okay, and in order to do that, we're going to create 2x2 unoriented gradients. All right, so let's do that. So we're going to create 2x2 unoriented gradients. Okay, so with this, what do we aim to do? Well, we, as I said, we want to aggregate graded information over larger spatial regions. And to get started, I just simply said a quite small region of 2x2. Basically, we're going to create 2x2 blocks here. So basically, what we're going to do is to create a pooling operation, right? So aggregation that is going to slide. So this 2x2 block is going to slide across the width and basically the tensor, and row by row. Okay, once a row is processed, it's going to move down to the next row, just like that, just like regular kernel operation, right? And yeah, there's no better way than getting started. And now to create these 2x2 unoriented gradients, we are going to utilize basically the initialization, or basically definition of previous operations. So more specifically, remember that we defined padding. We defined a padding in our original function. So if we have a look at here, this replication padding. Okay, we are going to utilize this one right now. Okay, so I'm actually going to copy paste it. Okay, I'm going to copy paste it, and we're going to utilize it. Right, formatting. Okay, great. That's one thing, and we are also going to use the block pool. Okay, so the block pool that we defined also in previous videos, these block pool, okay, both the layer and the, say, modified weights. Okay, we're going to use both, of course, and we are going to see in a second how are we going to be able to benefit from these. Okay, fantastic. Okay, and of course, number digit in our case, we just simply have NO. Yeah, and the rest also here, fantastic. Great. So now let's get to work. Let's see this in action. So first of all, we are going to define these 2x2 grids, these 2x2 blocks. Okay, and well, how? Well, we're just going to take the original cell that we defined above. Okay, these are the unoriented cell, and we're just going to multiply by itself. Okay, to get these squared unoriented block. Okay, to get started with. So let's get these squared unoriented gradients. Okay, so unoriented square, and I'm just gonna say, okay, so this unoriented cell by itself, just like that. Like that. Fantastic. And well, let's also visualize this. Okay, so let's print this, and we're gonna get block pool, this block pool, and well, yeah, exactly what we need to do. Let's just print the previous result. So squared unoriented gradients. Okay, so the unoriented squared like that. Okay, let's have a look at it. Okay, so this is just the result of multiplying the unoriented cell that we obtained above, which is this one essentially, and multiply it by itself, so that we got this result. Fantastic. So now, what is next? Well, let's get the we're gonna pad these basically squared unoriented cell, using, of course, the padding. So essentially what we're gonna say is, okay, we want now to pad, so unoriented squared, unoriented squared, and I'm gonna put padded, unoriented square padded. And now, how do we pad our unoriented squared? cell. Well, so just passing our unoriented squared through the padding. Yeah, in that way we are going to obtain the essentially padded unoriented gradient. So now it's going to be the padded squared unoriented gradients. Okay, let's see, fantastic, and on unoriented squared padded, great, and space here as well. So essentially, as you can see, we have the same. Let's see if we can get cleaner numbers. Yeah, that's what I wanted without, yeah, so small. Okay, so as you can see, we have the squared unoriented gradients, and in essence we still got them. So but now look at this, this is our core, right? This is our core right there. Great. And what this padding is doing is, remember, adding the number of columns and rows that we specified. Okay, so remember that these see where it is. Okay, here these nn dot replication pad to d, if we introduce just a 1, this meant that it was going to introduce a padding 1 in the row dimension and 1 in the column dimension. That is why we got 1 extra column at the beginning, 1 extra column at the end, 1 extra row at the top, 1 extra row at the bottom. And how does it work? Well, what it does is to copy the say value that is closest to the distribution. What I mean is that, so for example, here we have a 7.48, so this means that on the left, at the top, and at the top left corner, we're gonna get that exact number. What happens to the left neighbor of this value in here? Well, it's gonna be copied. And same story with the bottom left corner. Okay, same story that at the top left corner, and same strategy is followed around the tensor. Okay, fantastic. And also, of course, in the second say half of the tensor. Great. Now we just padded our original unoriented square tensor. So what is next for us? Well, we are going to aggregate the basically values that are in the, say, square oriented gradients. Okay, so to do that, we're going to apply the block pool layer. Okay, that's exactly what we're going to do. So let's see how it works. So we're going to so we want to get the aggregated squared unoriented gradients. Okay, and also let me put here, for sake of clarity, so get the padded squared unoriented gradients. Fantastic. So now we're going to aggregate these square oriented gradients, and well, we're going to say, okay, we're going to define aggregated unoriented gradients, and we're going to pass it through the block pool. And what are we going to pass through the block pool? Well, of course, the unoriented squared padded. Okay, so the padded unoriented squared gradients. Okay, fantastic. So now we're going to visualize. So just print, and we're going to say, okay, so aggregated squared unoriented gradients. Fantastic. So there's that. Okay, so let's have a look at what happened in here. So you see how we went from having these padded squared or unoriented gradients to these aggregated squared. But actually, to have a better understanding of how the shape changed, let's actually print it out, right? So let's print it out right now. So just for reference, put here the unoriented square padded and also print out the shape of the aggregated unoriented gradients. Right, let's see. So you see we went from having a tensor that has a 4D shape of 1, 2, 5, 5 to just have a 1, 1, 4, 4. Yeah. So what happened is that we essentially applied this aggregation, but how does it work really? Well, to understand that, we need to see what layer we're using to perform this aggregation, and that layer is the block pool. So the block pool, I mean. So the block pool is actually a convolutional layer that has an in channel of number of orientations, out channel of 1. Then remember that this was the kernel size, and that's all. Well, also the bias is set to false, but there's nothing else set. Okay, so this implied that essentially we would be using a stride of equal to 1, because remember, if we go to the PyTorch documentation, that if we didn't specify the stride number, well, by default it's going to be 1. So that is the key here. We are using a stride of 1. So we're using a stride of 1, and we, remember, just set a block of 2 by 2. Okay, so this implies that what we are doing here is the following. We are taking blocks of 2 by 2, and both basically the block and the upper side and the equivalent one in the other, say, side, the other half, and we are adding them together, so adding them up. Yeah, so to actually see that explicitly, so what we're gonna do is to just perform the sum right here. So for example, let's first perform the sum of this top left corner. Okay, so we're gonna take these 4 numbers and add them up to these 4, and we should get this number right here. Okay, we should get this number if we were correct. So let's have a look. So just realize that in this 2 by 2 block, the same number repeats 4 times, so we just need to add the same number or just multiply it by 4. Yeah, so let's actually put the calculator. So it's going to have 4 times this number, because it just happens that in this particular block we have 4 times the same number, and this is going to be added to these four numbers. Yeah, so again we have the same number, so we just need to take this one and multiply it by 4. So 4 times this, so 37.50. Okay, and yeah, exactly, we got this number up to the 3rd decimal place. Yeah, for whatever reason it's not giving us exactly the same number, but what matters is that we're getting essentially the same number. Okay, fantastic. So now how do we advance in this algorithm? Well, so now we're taking stride of 1. Okay, so this means that, remember, if we just specified one number for the stride, that implied that both for the horizontal and the vertical movement we would be applying that stride, right? The same stride for both movements. Yeah, so in this case it's 1 for both. So now let's just keep moving. Let's reproduce this row and also this number, just to see that also the vertical stride works. Yeah, so let's just do that. And now stride of 1. So now we need to move just 1 to the right. So now the block is conformed by these 4 numbers, right? So now let's do that. So we take this, and now it's just twice in that block, so 2 times this number, and we do the same here, because we have again this number twice. So let's take that, and yeah, so now we need to add that to the second half of the tensor. So that is, here we are having these 4 numbers. So again, let's take that and multiply by 2, and again we do the same with the number. So we get this 29.11. Okay, so exactly, that is what we get. Fantastic. So now let's continue with the algorithm. So now we again move to the right because we want to reproduce this number, say. Okay, so move to the right, and again this number is repeated twice, so we just 4.39. okay, is this exact number. Yeah, just take it from here. 2.49, and this will multiply by 2. And now we take this number, and same story. Fantastic. So now we go for the second half. So we go for this one, and again we have this number repeated twice. Let's just take it plus, and now we have this number right here. So take it and multiply by 2. Great. So now we have this 12.69. okay, which oh, wait a second, what happened? We should have something is wrong. Okay, so what we did was to we just moved to the right and multiply this twice, 4.3994. yes, and we did the same with 0.1145. 0.1145. oh yeah, that is why, because you don't add, you multiply here, of course. Fantastic. So now it's a 10.79. Fantastic. So as expected in here. Great. And now finally let's reproduce this number. So again, same story. Take this number, multiply by 2, then, well, actually now it's 4 because we are the top right corner, so we have the same number 4 times. So instead of 4, just put, instead of 2, put of 4. And same story here. We have the same number repeated 4 times, so 10.37. So 10.37, which is in here. Yeah. So just take this one and multiply by 4, and we get these 0.8728. Yeah, as expected. Again, we're not getting the 4 decimal place. It's fine. In essence, what we want to showcase here is that we're getting the correct number in essence. Okay, up to the 3rd decimal place at least. Fantastic. And now, just to wrap it up, let's verify that we get this number right here. And well, to do that, we need to move in the vertical direction, more specifically downwards. Yeah, so now we start always from the top left corner, and now we move downwards. So we move one straight downwards. So now we have this block right here. We have these two numbers, yeah. So again, we have this number. Well, we have a number repeated twice. So same story. Just take this one and multiply by 2, and now we have to do the same with this number right here. We multiply by 2. Fantastic. And now we do the same story here. So same story by 2, and finally we get these 1.8210, like that. Fantastic. So now we get 23.47, yeah, which is what we expect. Fantastic. So now we understand perfectly how this aggregated algorithm is working out. And now that we got these aggregated say tensor, what should we do? Well, now we want to actually get the norms of these unoriented gradients, because right now what we are working with are the squared of the magnitudes of our gradient. So we want to actually get just the magnitudes by itself. Okay, so to do that, we just need to take the norm. So let's put here get aggregated magnitude of unoriented gradients. Yeah, fantastic. So get the norms, and well, take the square root of the aggregated gradients, because these by themselves are the squared magnitude of the gradients, right? Fantastic. So now let's just have a look. So just print statement, and we're gonna say, okay, so the norms of the unoriented gradients are these. Okay, fantastic. So let's have a look. Yeah, so essentially we just took the square root of each element in here. So these are the norms of oriented gradients. Fantastic. So once we have that, once we have the magnitudes of the unoriented gradients, what should we do? Well, what we want to do now is to, first of all, we aim to place all our gradients, both unoriented and oriented, together. Okay, and well, and why do we want to do that? Because we want to gather all the information that we have, okay, in one place, yeah, and so that we can utilize it later in the algorithm. Okay, and essentially we are going to say place them all, okay, in a structure Yeah, and we also are gonna set the magnitudes of our gradients with and also we're gonna set an upper limit for the magnitudes of our gradients, and this is due to the fact that we want to avoid certain effects that are unrealistic, in the sense that, for example, if we are measuring the intensity of light, say, in a small region of an image, so some regions definitely are going to have are going to be brighter than others, but if certain region is too too bright, or basically is much brighter than its neighbors, this effect is going to overshadow the, say, less bright sides. Yeah, and this is going to make us lose information related to the less bright parts of the image as compared to the brightest, say part, right? So we want to, say, cut down the say difference, and we do that by essentially clamping the maximum, also basically clamping the magnitude, the upper magnitude of say certain gradients. Okay, but yeah, we'll see that how that, so we'll see how that works. Okay, but yeah, let's now start clamping. We're gonna start doing that. So let me place here and say clamping for stability. Okay. Fantastic. So now, as I said, we first need to place both unoriented and oriented gradients together, right? And how do we do that? Well, we concatenate both. Yeah. So let me write that down. So put unoriented and oriented gradients together. Okay. All right, so we're gonna place that, we're gonna call these, say, collection of both unoriented and oriented gradients as cells. Yeah, and we're gonna concatenate both. So we're gonna do the torch.cat, which we saw how it works in previous videos, and basically how it works is that in the first, well, let's actually recall that. So let me close that down. So these torch.cat. So essentially, remember that first it took the tensors that you wanted to concatenate, and you also specify the dimension. That you wanted to concatenate. And so by default, CDAT is going to do it in the rows. So essentially in this example, if we take this tensor as an input and we input it 3 times and we specify the dimension 0, of course it's going to do it 3 times. So 1, 2, 2, and 3. Yeah, in the row dimension. But if we do it in the column dimension, well, we'll do the same in the column dimension. So this is how torch.cat worked. And well, so we need to specify the tensors that we want to concatenate, and remember that in our case we had unoriented. So we had these, we had the original, say, tensor, which was up in here. These are random cell, because remember that this tensor was, say, the tensor that we started with, and we're going to concatenate this one, because remember this one is the oriented tensor, in the sense that it contains the oriented gradients, right? And now we need to concatenate it with the unoriented. okay, which we called let me think. Did we? Yeah, because I'm thinking about whether it's the squared or just the unoriented, what makes more sense. Well, what it makes more sense actually is to place the unoriented cell, of course, because it's here where we combine both, say, positive and negative orientations, and adding them up, that results in having unoriented gradients. So definitely it's going to be this one, okay, and not the squared one. Okay, so this one right here, and we want to concatenate in the column dimension. Okay, we're going to do that in the columns, also with respect to the columns, and not with respect to the rows. Okay, so just let me place here one. Great, and let's just have a look now on how this is going to be structured. So print and place unoriented and oriented gradients together, and okay, so there we have them. Okay, we have the yeah, let me just, for reference, let me just print them out so that we can see them and compare. So let me print here before random cell and an oriented cell. Okay, so as you can see, I remember that the numbers keep changing because we are dealing with a random tensor. So essentially we have these two, not well, let me actually, because like that is a bit messy. So unoriented cell, let me place it in a new line. Fantastic. So essentially what's happening is that we want to place these two tensors together, in the sense that we're going to concatenate them in the columns. So basically what we get is that these two tensors are going to be concatenated or placed into one, which is this one right here. Okay, so that is essentially what is happening. Oh, fantastic. So now what should we do next? Let's think about that. Well, we are going to need to normalize, yeah, the magnitude of the, say, aggregated or the gradients, more specifically the say norms of it, right? So in order to do that, well, we're going to define a factors variable, yeah. So we are going to normalize dividing by the magnitude of the aggregated unoriented gradients, yeah. So factors, and the normalization factor is going to be basically the inverse of the magnitudes of the gradients. Okay, So that is what we called norms. Yeah, norms. Great. So now, what should we do next? Well, now we need to be careful because remember that we applied padding earlier. Okay, so remember that here we padded our unoriented gradients, right? And this meant that we expanded the spatial dimensions of the gradient tensor. Okay, so this means that new rows and columns around the tensor were created. Okay, and this was done because of pooling, because we wanted them to apply the say a block pool layer. Okay, now we want so basically these modified the arrangement of the gradients now, right? And what we want to do now is to recover the original arrangement, okay, prior to this padding. So to do that, we scale the gradients with factors, and more specifically, we're going to take slices. Okay, so we'll see how that works later, like right after. So yeah, let's actually get started with that. So to see how it works, let's print them out explicitly. So let's get factors slice, and with this we're going to get rid of certain row and column. So say X row and Y column. What do I mean by that? Well, so we're going to be printing them out so that we can see what's going on. So factors slice, we're going to have factors, and we're going to have everything. And now, okay, let's start by getting rid of the last row and the last column. Okay, we're going to start doing that. And how do we do that? Well, we are going to say, okay, we want to take everything up to the last element in these dimension, which are the rows. And same story with the columns. Great. And let's visualize that. Okay, so what happened is that for the factors, because remember that, well, did we print factors actually? No, we didn't. So we also want to print the factors so we can compare. So the normalization factors. Like that, factors, and like that. Okay, so see what's going on here is that we are just taking a slice of the normalization factor tensor. Okay, and as we removed the last row and the last column, well, we removed this one and we removed this column right here. Okay, so we are left with this block of 3 by 3, which is exactly what we get in here. Okay, and remember that this is a 3 by 3 structure. Okay, say was the original one prior to taking the padding, because remember, have a look, our say halves, both of them were 3 by 3. yeah, before the padding. But after the padding, well, we get a 4 by 4. Yeah. So now what we are aiming to do here is to recover these, say, original structure right there. Okay. Or better say, what we want to do is to take these 3 by 3 structures to then apply them to the actual, say, concatenated tensor that contains both, say, unoriented and oriented gradients. Okay, so remember that for the cells we had this, so these, we place them together here. So we have these tensor right here, and have a look, we are having 3 by 3 in each block. So if we aim to, because now these are not normalized, okay, and how do we normalize them? Well, we're going to be multiplying by the normalization factor. But the normalization factor as it is right now, well, it has dimensions that are not going to be suitable for multiplication with these tensor right here. Why? Because we're having a 3 by 3, we're having a bunch of 3 by 3 blocks, yeah, while here we have a 4 by 4. So we need to be multiplying all these blocks by 3 by 3 as well, otherwise it's not going to work. That is why we want to take say blocks of 3 by 3 to then apply them to these say concatenated tensor containing both unoriented and oriented gradients. Fantastic. So, and to do that, well, we cannot miss information from the normalization tensor. That meaning that we need to take into account all the, say, numbers that are placed in this normalization tensor. So right now we have taken this 3 by 3. So the strategy is the following. The strategy is to now to move, say, one column to the right, and now we're going to take just this 3 by 3 block. So we're going to get rid of the first column and we're going to get rid of the last row. Okay, so we do the same. So same strategy, but now we're going to get rid of the first column. So how do we get rid of the first column? Well, now we say, okay, we want to start from the first and till the end. So we get rid of the first column, and we want to now, because we move to the right, we want to get rid of the last row. Okay, fantastic. So that is what we're going to do now, and have a look. Now we have these 3 by 3, so 0.31 and so on, as you can verify that these 3 are these 3. Fantastic. And what do we do now? Well, remember that we also need to take into account the numbers of the last row. Okay, so now we move downwards, and now we're gonna get rid of the first row and the first column. Okay, that's what we need to do next. So that's what we do. First column, and so first row, and get rid of the first row and get rid of the first column. Yeah, that was correct already. Fantastic. So let's verify. So again, we are taking these collection of numbers. We're taking these 3 by 3. That's right there. And well, what is the last block that we are missing? Well, we're missing this one. We're missing this one, so that we can take into account this 1.4259 number, yeah, which was not taken into account previously. So how do we do that? How do we get this block? Of course, we get rid of the first row and get rid of the last column. So let's just do that for completeness. Get rid of the first row and get rid of essentially the last column. So to get rid of the last column is everything except the last. Okay. Fantastic. So now we have indeed this block right here. Okay. Fantastic. So now what we want to do is to apply this normalization to the original, so to the clamped to this tensor right here, so that we obtain the normalized, unoriented, and oriented gradients. Okay. But again, remember that what I mentioned before, that is that we want to set an upper limit. We want to set an upper limit so that we don't get too much of a bright contrast, we could call it like that. And to do that, we are going to clamp. We're going to need to clamp our tensor. So what we're going to do is to clamp it with say default value of 0.2. Okay. This is just by design. Just place it like that. And how are we going to structure our data, or say normalized data? So essentially what we're going to do is to because right now what we have, if we multiply, okay, if we multiply say these factor slice by these entire cell, so this entire placed unoriented and oriented gradients as they are right now, we're just gonna get the contribution that is related to this upper left corner. Okay, so what I mean is that we need to multiply these factor slice by the say concatenated tensor, and add to that number the multiplication of the next factor times the same essentially the same concatenated tensor. Okay, and with that we do that with all our factor slices. All right, we're gonna add them together, and we are going to say take an average, an estimate of these sum. So basically what we want to do is to have an average. We want to have an average contribution of every gradient. Okay, we are averaging them all in the same way. So essentially it's like taking the average of the gradients, of the magnitude of the gradients, both unoriented and oriented, and both treated in this on the same ground. So basically treated as they were equal. Yeah, and well, so what we're going to do is to actually add them together and take the average. We're not going to take the, say, a strict average of adding the four of them and divide them by 4. We're going to take an approximate average just by multiplying the sum by 1/2. Okay, just because it's, say, the quick way to take the average is not basically the most precise method. Of course, the precise method would be to take just the average, but for the purpose of this practice, of this practical, it's okay to just take the average just by taking the resulting sum and multiplying it by 1/2. Okay, so let's just proceed, and we're going to basically we're assuming that each cell is contributing equally. So basically we're assuming that each collection of magnitudes, of gradient magnitudes, is contributing the same way to the final, say, map or feature map. Yeah, but again, let's see it in action. So we are going to assume that each cell contributes equally to the overlapping blocks, and we are going to use this half heuristic factor. We're going to use it as an heuristic factor. okay, to then scale down the combined result. So basically we want to not have huge differences between all the grading contributions, okay? So having a 0.5 multiplication is going to scale down the combined result, okay? So yeah, let's define this, and what we're gonna do is, yeah, what we just said, we're going to multiply the original concatenated tensor by the factors, okay? So take this factor, okay, and well, remember that we're going to clamp it, so we need to include this within clamp, and we are going to place an upper bound of 0.2, okay? Fantastic. So what we're going to do is to basically add this to the other 4 contributions, okay? Equivalent contributions. So now what we do is basically get rid of the last row and the first column. Okay, and same story here. Now we get rid of the first row and the first column. Yeah, fantastic. So, and we get rid of the first row and the last column. Fantastic. So, and now remember, we take this heuristic factor to scale it down, to scale down the result, like that. And yeah, we should be ready. So exactly right now, so let me place here, so print it properly, so print, and we're gonna have like that and like that, and I'm gonna say so scale down contributions of unoriented and oriented gradients. Yeah, great, fantastic. So yeah, there we have them. We just have this contribution, and yeah, in a way that essentially yeah, basically in a way so that there's no huge contrast between, say, extremes, right? So you can see that the numbers, they don't differ massively, so that this structure will allow us to obtain a result that is not going to overshadow certain regions of our map, okay? But yeah, that is all I wanted to discuss in this video, and I am willing to see you very soon.